So this video continues on with this idea of goodness of fit, and the purpose is to look at the code. We're just going to look at the code. In the previous video we considered the concepts, and in the next video we'll think about the results and the interpretation, but in this video the focus is on the code. So here's our model statement. Got this keyword model, the open quote, the open curly brace, close curly brace, close quote. And in the very first video, we went over this portion of the model statement. And so for the time being, we're not going to think about this. In this video, what we're going to do is think about this part of the model statement. So I've taken this part of the model statement and I've just enlarged it here, and now I want to go over it. So the first thing we're going to have is we're going to have a loop. This is going to define a loop, and it's going to loop across years. It's going to loop across the 16 values of year. There's the open curly brace and the closed curly brace of this loop for those 16 years. And it's going to begin by calculating a residual as the difference between pop size I and mu I. And what's that all about? So remember the way Gibbs sampling is going to work. In each of our 9,000 iterations, we're going to get values of alpha, beta, and tau. And so pop size is the observed population size for year I. I goes from 1 to 16. What is mu I? Mu I is determined here. We see it in the likelihood function. Mu I is alpha plus beta times year I. So we've got alpha and beta for that iteration, and we can just use this to come up with our calculated value of mu I, like that. So if we come down here and look at this plot, what are the residuals? The residuals are the differences between pop size and mu I. Well, our mu I's are those round dots, so they define the line of best fit. So there's our mu I's, and our pop sizes are these open circles here. And so the residual is just the difference. Clean this up a bit. The residuals are the differences between the pop size values and the values of mu I. So we're going to determine those residuals, and then we're going to square them. So square I for each year I, square I will be this distance squared. Now let's think about y nu I. Where does that come from? Well, remember we've got alpha, beta, and tau. We define mu I as alpha plus beta times year I. So we got mu I, okay. Then we're going to assume, maybe a better way to say it would be, what we're going to do is we're going to generate new values of y, new values I'm going to call y nu I, and we're going to get them as single random samples from a normal distribution that has a mean of mu I that's determined by these guys, and a precision tau, which will be the precision that we have for that particular iteration. So if we come down here and look at our plot, y nu I are these squares, these solid squares. And so each one of these solid squares is our y nu I. And then what we're going to do is we're going to take the difference between those y nu I values and mu I, and we're going to square them. So we're going to take each one of these distances, each one of those distances between y nu I and mu, and we're going to square them. So all of that is going to happen within this loop for the 16 years. And then we're going to exit our loop, and we're going to begin by calculating this value called fit. So remember what happened up here. Up here, we got these values of square I. So what were they again? What they were is taking each one of these differences between pop size and mu, each one of these pop size versus mu differences, and squaring them. And so what fit does is it just sums all these square distances. It just sums them over all years. And a similar thing is going to happen with fit nu. Where did fit nu come from? Well, again, we've got these values of square nu I. What is square nu I? Square nu I arises by taking the difference between y nu I and mu I. So we take these differences, y nu I and mu I, we take those differences and we square them. So that's what we did before. And all we're doing here is to say, okay, we're going to sum up all those square differences over all 16 years. Okay. Then we're going to calculate this BP value using the step function. And we saw how the step function worked before. It's pretty simple. We've got these values. In each iteration, we'll have a value of fit, and we'll have a value of fit nu, and then we compare them. And if fit nu is greater than fit, then BP value will be equal to 1. And if fit nu is less than fit, then BP value will be equal to 0. And then finally what we're going to do is we're going to come down here and we're going to have another loop. And once more, we're going to be looping over a year. So we're going to loop over the 16 different years. And in each of those 16 different years, we're going to calculate a value of check, and it's going to use a step function, and it's going to be based on a comparison between y nu I and pop size. So if we come back here and look at this plot, where do we see that? What's the difference between y nu I and pop size? It's the difference between the solid squares and the open circles. So that distance there, and that distance there, and that distance there, and that little distance there, that little distance there, and that little distance there. And again, as always, we had the step function. We know how that works. If y nu for any one year is greater than pop size for that year, then the value of check for that year will be equal to 1. In contrast, if for any one year the value of y nu is less than pop size for that year, then the value of check for that year will equal to 0. So that's just an overview, what we've got in this video, of all this code. In the next video, what we'll look at is some of the results and the interpretation.